Greetings, this is Greg. The Lockheed P-38 Lightning was one of the best and most versatile airplanes in World War II. I think most aircraft enthusiasts know that it was a successful fighter, especially in the Pacific and the Mediterranean theaters. I think fewer people know that the reconnaissance versions of the planes were very successful in their role. A statement on the Lockheed Martin website says that the recon variants, quote, obtained 90% of the aerial film captured over Europe, unquote. There were many other variants of the P-38 as well. For example, a night fighter version that had a two-man cockpit, was radar equipped, and had some other changes to help keep it hidden in the darkness. As with most fighters, the P-38 could and did drop bombs. It could carry a 4,000-pound bomb load, and one source has its maximum bomb load at 5,200 pounds. There was also a specific bomber variant that had a glass nose, a two-man crew, and the Norden bomb sight system. Another version of that bomber variant used a ground scanning radar system to enable it to bomb through overcast layers. Even a torpedo bomber version was considered, at least considered. This picture shows the plane carrying dummy torpedoes for testing, and the weight and balance data for the plane does include torpedo payloads, but as far as I know, it never actually operated as a torpedo bomber. There was even an air ambulance configuration which could carry two patients in external transport pods. I'll cover all of these variants and the degrees to which they were used and the successes and failures in follow-up videos. But in short, the P-38 could perform, and perform well, every type of mission that could be expected of a World War II fighter. Now some might say, well, big deal. In that era, there were a lot of twin-engine airplanes that performed multiple roles. That's true, but the difference is that during that era, most twin-engine fighters proved incapable of fighting enemy single-engine fighters, and thus were relegated to these alternative roles like night fighting and ground attack. That was not the case with the P-38 Lightning. It was competitive with enemy single-engine fighters throughout the war and was employed in other roles due to the plane's versatility. In regards to a twin-engine plane that really couldn't compete with single-engine fighters in air-to-air combat, the most classic example I can come up with is the Messerschmitt Bf-110. I'm bringing up the 110 here specifically because it's one of the two planes that were constantly being compared to the P-38 in documentation from that period. Both planes have powerful liquid-cooled V-12s. They're both obviously twin engines. They both have twin tails. As you can see in this identification slide, they actually look quite similar from the front. The other plane that was often compared with the P-38 was the British Mosquito. I don't need to go into too much detail on this right now. I did talk about it a little bit in my Mosquito video, but I'll be covering this comparison a lot more as this series continues. If you haven't watched my Mosquito video yet, you may want to after this one. Let's get into the topic at hand, the P-38 Lightning itself. I want to cover the plane's main design features. In other words, this video is going to be a fairly basic overview, at least by this channel standards. The P-38 was Lockheed's answer to a U.S. Army Air Corps proposal made in 1937 that called for a high-altitude interceptor, they used that word, interceptor, capable of reaching 360 miles per hour and capable of climbing to 20,000 feet from sea level in 6 minutes. Now, this was a very tall order in 1937. Lockheed wanted not only to design a plane to reach these relatively lofty goals, they wanted to exceed them by building the first fighter plane to be capable of reaching 400 miles per hour in level flight. At the time design work started, there were no aircraft engines powerful enough to enable a single-engine fighter plane, not a race plane, but a fighter plane, to reach that speed. Thus, Lockheed had to use twin engines to comply with both the Air Corps proposal and their own goals. The project was a huge undertaking for Lockheed, not only because of the extreme for the time requirements, but more significantly, much more significantly, and I think a lot of people overlook this, but because Lockheed had never built a fighter plane before. In fact, they had never built any true combat airplane. They had built planes for the civilian market, some of which, like the Vega shown here, were purchased by the military, but they were not combat airplanes. The Vegas were fast. Lockheed had some pretty good knowledge about how to make airplanes fast. In fact, the Vegas were about equal in speed to contemporary fighters from the mid to late 1920s. The Vega also had tremendous range and altitude capability. So Lockheed had a good handle on performance in terms of speed and altitude. They also understood multi-engine aircraft, and they had built the excellent Model 10 Electra in 1935. It would do about 195 miles an hour. So, jumping from sub 200 mile per hour civilian airplanes to a 400 mile per hour fighter was a tall order, and as you might expect, there were some bumps in the road, which we'll be talking about. But first, let's cover the basic design of the P-38. The most striking feature has to be the twin boom layout, so let's start there. Why build a twin boom fighter? It certainly wasn't the norm. It wasn't the only option, though, that they considered. These are sketches from Kelly Johnson, one of the 38's primary designers. The sketches show that multiple configurations were considered. Before we get into them, I want to say that there had been other twin boom airplanes before the Lightning. In World War I, Caproni built bombers with twin booms. In the late 1930s, Fokker had the G-1, which was a decent airplane. Hughes had the D-2. Some say that the P-38 design was stolen from Hughes. I don't think that's likely. I think it's more likely both design teams simply reached the same conclusions when looking at the data requirements and available engines of the time. Of course, after the war, we had a lot of twin-boom airplanes, both fighters like Britain's excellent de Havilland Vampire, seen here, and cargo planes like this C-119. Of course, both of these use twin booms for very different reasons than the P-38. So let's get back to those sketches from Kelly Johnson to get an idea about why Lockheed chose this design. I'll go through these pretty quickly. This one is what I'll call a conventional twin-engine airplane with engines mounted on the wings, like this B-26 Marauder. This is the layout that has been used by the vast majority of twin-engine propeller-driven airplanes from World War II up until today. Normally, if you're going to design a twin-engine prop-driven airplane, this is going to be your go-to configuration. Now these two are interesting. They have twin engines mounted in the fuselage with some sort of mechanism set up to drive propellers that are out on the wings. One example has rear-mounted pusher props. Now, as far as I know, no production airplane has ever flown with either of these configurations. And even without the complexity of those prop drive mechanisms, I don't think these designs would have worked out for reasons which will become apparent. This one is a twin fuselage design, which should not be confused with a twin boom design. It's not the same thing. The twin fuselage layout was famously used on the P-82. I have to say I find this idea a little bit disturbing. I feel that if I flew such a craft, every time I looked out to one side, I would feel like I'm flying too close to another airplane. Personal feelings aside, no question that this worked. The P-82 performed pretty well. So that leaves us with this one, the push-pull design using twin booms. There have been planes like this, and they can perform pretty well. But the downside is that once you put two engines in the fuselage and then whatever else you need, armament, seats, or whatever, there's not a lot of room left. For example, the Cessna 337 has the push-pull layout and twin booms. It's a wonderful airplane. I have flown one. It has plenty of performance, great flying qualities, some real advantages over a conventional twin. However, it's very short on baggage space for a six-seated airplane. In my view, it's that lack of space in the fuselage that really kills off, well, these three contenders right at the start. Why? Because of the turbocharger. Turbocharging systems took up a lot of space in the 1930s and 40s, and these three configurations just don't have any place to put all the needed components. Now, why bother with turbochargers? Well, because Lockheed was going to need to use some form of secondary supercharging or second stage supercharging on the P-38 in order to get the desired performance, and that really had to be a turbocharger for several reasons. The chosen engines were Allison V1710s. They have a gear-driven centrifugal supercharger built into them, but it's just a single stage and not capable of delivering power at high altitude, which the 38 was going to need. The P-38 was going to need to have power throughout a wide range of altitudes. Second stage was going to be needed to do that, and Allison didn't have a second stage mechanical supercharger for their V12 at this time. In fairness to Allison, neither did Rolls-Royce, Daimler, or any of the other aircraft V12s in production in 1937. Allison hadn't bothered with a second stage mechanical supercharger because the Army Air Corps was going all in on turbochargers. I have a whole video explaining the history and reasons for that, the technical reasons, but the short version is that NACA had determined and published in this report that a turbo, which was called a turbo supercharger at the time, to mesh with modern parlance, I will frequently just call it a turbo or turbocharger. In any case, the turbo supercharger had significant advantages over a mechanically driven supercharger. The Army Air Corps really latched on to the information in that report and wanted turbos for the second stage on high altitude airplanes, as evidenced by the fact that nearly every high altitude U.S. Army Air Corps plane in development around this time and up until U.S. entry into World War II was turbocharger equipped, including the B-17 Flying Fortress, B-24 Liberator, the P-43, which was a predecessor to the P-47, the P-47 Thunderbolt, and the P-39 Airacobra, although the Airacobra was not produced with its turbo, and thus it turned into a low-altitude airplane. And, of course, the P-38, which has turbochargers. This means Lockheed had to use the turbos for three main reasons. First, they needed a second stage to get the performance they wanted throughout that altitude range. Also, the Army Air Corps wanted turbos. And lastly, there was literally no other choice for the Allison V12. The need for turbos eliminates these three designs because you simply can't fit the turbo systems in there. I'm not sure why the twin fuselage design was eliminated, but I think it was due to weapon placement concerns. I'm basing that on the fact that Lockheed mentions the P-38's weapon configuration a lot in period publications. They were very proud of the centerline mounted weapons. The twin fuselage design would not have allowed that much firepower to be placed right in front of the pilot. So what about what I'm calling the conventional layout? Well, it certainly proved itself in nearly every role in World War II. In typical fighter versus fighter combat, it usually didn't work out that well, but in just about everything else, this design excelled. So why not the conventional configuration? Well, I think that answer is going to be self-evident as we go over the plane's design. So let's take a look at this cutaway diagram to get a good idea of how everything's laid out in this airplane. Let's look at those twin booms. At the front, we have a Curtiss Electric constant speed propeller. Right behind that, we have an Allison V1710 liquid-cooled V12. And on the left boom, and we're talking about production airplanes right now, the prototypes are a little different, but on the left boom, the prop rotates counterclockwise as seen from the rear. On the right boom, it's clockwise, which would be the normal rotation for an Allison and most U.S. fighters during the war. I'll get into propeller rotation later. There's actually a lot to talk about with that. The booms are quite large. People underestimate how large these things are. Each one is about the width of the fuselage on a typical V-12 powered fighter. Look at just about any other late 1930s fighter and you'll see that the point of maximum width on the fuselage is usually where the exhaust stacks are. The exhaust stacks on a V-12 are the limiting factor in regards to minimizing width. The P-38's exhaust stacks are enclosed in the booms, so each boom is about the width of a typical fighter that's powered by an Allison V-12, like the P-40 pictured here. Under the engine we have two oil coolers, which are fed from air scoops at the front. Now this is a later P-38 because I don't have a cutaway diagram of an early version, at least not a good one. A key difference is the intercooler configuration. A later P-38, much like this airplane, much like a P-47 Thunderbolt, takes in air from below the engine in a scoop that's divided into three sections. The two outboard sections direct air to oil coolers, and the center section delivers air to the intercoolers. Now, the early 38s are quite a bit different. They have wing-mounted intercoolers, which is why they only have the two scoops, the twin scoops, under the engines, and those, of course, are for the oil coolers. Now, just aft of the engine, we have the oil tank for the dry sump system. It lubricates the engine. And that's about even with the wing's leading edge. Near the trailing edge of the wing, the boom contains the turbocharger, aka turbo supercharger, aka turbo. Of course, it still has a mechanically driven supercharger at the back of the engine, but we can't see that in this diagram. In between the oil tank and the turbo, so in between the leading edge and the trailing edge of the wing and the boom, there is a lot going on. Not only do we have the wing structure there, but this area also houses the main gear retraction mechanism, exhaust piping to the turbo, charge air piping from the turbo, coolant lines, oil lines, and more. This is a very busy area. Aft of the turbo, we have a space for the main landing gear wheel when retracted. Aft of that, an oxygen bottle, two cooling system radiators, and another oxygen bottle. Just aft of that is the battery. On the other side, the other boom is pretty much the same. There are some differences. I already mentioned engines and props rotate in opposite directions in a normal US production variant. Also, the left boom has the battery. The right boom doesn't have a battery. In that same area of the boom, it has a little cargo compartment. You can't put much in it, but it's there. Oh, and the right side wheel well holds a hand crank for starting. There are other minor variations as well. You might be starting to see the reason for the twin boom design. In order to get all that stuff into the boom and minimize the cross section by not putting much stuff side by side, the booms have to be really long. So long, in fact, that minimal extension is needed to interconnect them with a tail. In this magazine, we have an article written in 1944 by Hal Hubbard, the vice president and chief engineer at Lockheed during this time. Kelly Johnson was working for Hal Hubbard, under Hal Hubbard, I should say, during the P-38's development, so I think this is a pretty good source. I'll be using a lot of screenshots of this article, but I'll post it in its entirety in the Patreon section. It's pretty interesting. Not just the article, but the magazine. It's shocking how many ads were in World War II era aviation magazines. Just as a point of interest, most of the pages are mostly ads. We'll be focusing on the article by Hal Hubbard, the first page of which is on the right side here. Each page in the article itself is free of ads, or I suppose you could say that the entire article could be considered an ad for Lockheed. Let's see what Hal Hubbard has to say about the 38's design. I'm paraphrasing here, but he points out that the two engines were needed to reach the performance goals. There just wasn't a single engine powerful enough to do the job in 1937. The armament was packaged in front of the pilot in the fuselage. This was where the designers thought it would be most effective. Every time I read something from Lockheed about the 38, they almost always mention the weapons configuration. In fact, it's mentioned at least 3 times in this article alone. Regarding the twin booms, and again I'm paraphrasing, but he says that once everything needed was put into the booms, turbos, landing gear, and so on, that they were so long that extending them a bit more to carry the tail just made sense. He also points out that there isn't really a specific advantage to a twin boom design, so again, it was all about packaging. Let's go back to our cutaway drawing and finish going over the airplane. The main portion of the wing is not anything exotic. It's a NACA 23016 profile, which was used on various other airplanes. The same profile was used on the Douglas DC-4, aka C-54. It seems to me that Lockheed was trying to go well beyond the requirements of the 1937 proposal from the Army Air Corps, not only by getting it up to 400 miles per hour, which of course was much faster than the specified 360 mile per hour speed in the proposal, but I think Lockheed also wanted it to have enough maneuverability to combat enemy fighters, hence the wing choice. The P-38's wing gives it a relatively low stall speed for an aircraft with such a high wing loading, and that's a key factor in determining turn performance. To make the wing even more effective, the designers gave it Fowler flaps. Fowler flaps extend in a way that increases the wing area and adds a lot of lift relative to the amount of drag they cause, especially at intermediate settings. Most fighters of the day, like this P-40, had split flaps, which didn't add much lift but did cause a lot of drag, and that was actually the point. They added enough drag so you could point the nose down and descend to the runway without increasing airspeed. That's bullet point 2 here from the FAA. Split or even plain flaps just don't add a lot of lift. Fowlers, on the other hand, do add a lot of lift. Let's take a look at some comparison numbers of stall speeds, flaps up and flaps down, to see how effective the P-38's flaps were. All the P-38 pilot manuals for all the variants show the same numbers. At 15,000 pounds, which is about where we would be for air-to-air combat, the stall speed indicated flaps up, power off 94 miles per hour. With flaps down, power off at 69 miles per hour. Those speeds are, of course, indicated airspeeds, meaning what's read right off the cockpit airspeed indicator. Of course, those numbers are pretty meaningless for comparison to other airplanes until they are corrected to calibrated numbers. The P-38's manual doesn't have calibrated numbers that go low enough for us to figure this out. Plus, there were 2 different pitot tube locations on these planes, which further compounds the issue. Thankfully, the Army Air Force Materials Center did some testing on a 38 at 14,800 pounds, close enough, and got us exactly the information we need. They found that the calibrated stall speeds were 112 miles per hour with the gear and flaps up and 88 miles per hour with them down. With the flaps down and gear up, it's 86 miles per hour calibrated. I really wish I had that data for all World War II fighters, but we just don't. A lot of times I have to sort of take an educated guess. Anyhow, power on stall speeds in the P-38 are dramatically lower than the power off stall speeds due to the accelerated slipstream over the wing and flaps. As you can see, even with only 25 inches of manifold pressure, and that's not much, the flaps down stall speed drops another 13 miles per hour. That's huge, and I'm going to talk about this factor later in greater detail when we get into maneuverability. Let's see how the stall speeds compare to the Spitfire Mark V with its split flaps, the P-47, which has slotted flaps, and I'll also add in the de Havilland Mosquito and P-51, both of which have conventional plain flaps. Not many World War II fighters have a lower stall speed than the Spitfire Mark V. Its numbers are 73 miles per hour and 64 miles per hour, as can be seen here. The manual does have numbers for calibration, but they only go down to 100 miles an hour. I'm going to have to interpolate off the chart here, and that's not ideal, but it's the best I can do. I figure we need to add about 6 miles an hour to those numbers, so we get 79 and 70 miles per hour. Using the same methods for the P-47, we get 115 and 100. For the Mosquito, we get 105 and let's call it 95. For this variant of the Mosquito, I cannot find any airspeed correction data, so Either it didn't need it because its airspeed indicator was dead on all the time, which is incredibly unlikely, or maybe I just can't find it. So I'll have to take the Mosquito's indicated numbers and consider them as calibrated. Um, Also note that the Mosquito's weight is a bit higher than it would be if it was going to be set up as a fighter airplane. But that's okay. I'm not trying to compare aircraft performance just yet. When I do, I'll even out the weights and hopefully I'll have some better calibrated stall speed data for the Mosquito. Right now, we just want to see the effects of the P-38's wing design and the Fowler flaps. So here are the numbers. Notice the P-38 has the highest wing loading here, yet even with flaps up, its stall speed is slightly lower than the P-47's. That's a benefit of the P-38's NACA wing. Of course, that wing has its downsides too, which we'll cover later. Take a look at the flaps down numbers. The Fowlers make a big difference, much more so than the split flaps on the Spitfire or the plain flaps on the P-51. The Thunderbolt slotted flaps are about in the middle. Better still, the Fowler flaps can be put halfway down into the maneuver position. This gave a lot of extra lift with little drag. That's kind of the point of Fowler flaps. Most P-38s, including all G models and later versions, had this maneuver position on the flap handle. All the pilot had to do was put the flap handle there and the flaps went to that position. On earlier P-38s, the position was still selectable, meaning you could still position the Fowler flaps to be optimal for maneuvering, but it required an extra step because there wasn't a designated maneuver position on the handle. On these earlier planes, the pilot had to put the flap handle to down, observe the flap movement, and then when they reached the point you wanted, which was about halfway, put the handle back into the closed position. So what I'm saying here is that all P-38s effectively have maneuver flaps. It's just a question of whether it's a specifically labeled point on the flap handle and how easy they are to select. The takeaway should be the P-38's wing was not super special. It wasn't a low drag wing or a really high speed wing. It was sort of a jack of all trades wing. And with the maneuvering flaps out, the P-38 could really turn. It could actually outturn a lot of single engine fighters due to its low stall speed. Back to our cutaway drawing, let's talk about aerodynamic drag for a moment. I'm just going to talk about the total drag in this video. I'm not going to break it down into various types, not for now. The P-38 has quite a lot of total drag, not just because it's big, but because the design work happened to start in 1937 and a lot was learned in the next few years. Lessons the 38 was just a little bit too early to benefit from. For example, take a look at those exposed turbos on top of the booms. NACA discovered just how much drag exposed turbos would cause, and it was considerable. They came up with a fairing to enclose turbos while still allowing for enough cooling, exhaust flow, etc. Now that fairing was used on the P-47 Thunderbolt. In short, there was a lot of data from NACA coming out about reducing drag, and that benefited the P-47 and the P-51. But the P-38 was just a little too early to take advantage of it. On the subject of drag, if we look at the plane closely, you'll see all kinds of little air scoops on the booms. Zooming in, we can see a scoop on the side of each engine nacelle. This one cools the exhaust manifold, and there are a total of 4 of these on the airplane. Exhaust manifolds on a turbocharged engine get hot, and the P-38's cowlings don't have a lot of room in them, so these cooling scoops were needed. Notice these little tiny scoops. Again, there are 4 of them on the airplane. These cool the spark plugs, which get hot due to their proximity to the exhaust manifolds. These scoops connect to little tubes called blast tubes. They blast ram air onto things that they need to keep cool. There are quite a few of them on the plane, and they also cool the magnetos and tach generators. On the tops of the booms forward of the turbos, we have more scoops. These are also connected to blast tubes, and these cool components of the turbos. Then we have this big scoop under the trailing edge of the wing. This provides ram air into the turbo. In other words, this is the scoop that provides air that's needed for the engine to run. It's not for cooling. Interestingly, the P-38 has two sources of inlet air for the turbochargers. This ram air scoop is the normal source, but in most versions of the plane, the pilot can select filtered air to come from the wheel well. This will cost a little bit of power, but it will protect the engine by only letting in filtered air. This is great if operating off of a dirt runway. Certain P-38s have this selection slaved to the landing gear position. In other words, gear down, you get filtered air, and with the gear up, you get ram air for more performance. A lot of fighters of the period required additional components to get a decent amount of air filtration for operating in rough conditions. These usually robbed some of the airplane's performance, but that's not the case with the P-38. It gets the best of both worlds in that regard, and it's built right into the airplane, so that was pretty forward thinking of Lockheed. Aft on the booms, we have the radiators for engine cooling, and we have 4 of them back there, and they're big. All of these scoops, the exposed turbo plus the wing design and the overall size of the P-38, as well as some other things we'll talk about later, mean it has quite a bit of total drag. At some point, I'll get into the P-38's drag in more detail, but for now, just know that while it looks very sleek, it really isn't, at least not by U.S. fighter plane standards. As evidence of this, consider that a P-38D, which is an early model with 1,150 horsepower per side, that airplane at 5,000 feet will have a maximum true airspeed running flat out 322 miles per hour. Now that's not bad, but comparing it to other 2,000 horsepower fighters, it's not that great, and that's because of all the drag. For example, the early P-47B Thunderbolt will go about 20 miles per hour faster, a little more, a little less, depending on propeller type, and that's with 300 less horsepower. And we don't normally think of the Thunderbolt as a plane with low drag, although actually the Thunderbolt is pretty slick for how large it is. But the P-38 is not a low drag airplane, that's my point. None of this means that Lockheed wasn't trying to minimize drag. They were. External surfaces were flush, they were butt jointed. It was the first U.S. fighter to be built this way. It also utilized flush riveting in some sections. It's just that the size, the frontal area, and all of those cooling scoops, as well as some other things, added a lot of drag. Now I want to talk briefly about the cockpit section. In some period manuals, they call this the gondola, sometimes the fuselage. I think I'll go with gondola and try to use that just for the sake of continuity. The gondola houses from front to back the main armament, cockpit, radio equipment, and at the very back, hydraulic reservoir. Speaking of hydraulics, like most U.S. fighter planes, the P-38 had a hydraulic system. This is in addition to the hydraulics that operated the brakes. That's a separate system, and that was pretty standard on warplanes by this point. But we're talking about the main hydraulic system, and that operates the flaps, landing gear, radiator coolant shutters, and more. Some airplanes it does cannon charging, some airplanes it does aileron boosters. There's a engine-driven hydraulic pump powering this system on each engine, thankfully. If it only had a hydraulic pump on one engine, then if you lost that engine right after takeoff, it would be a disaster, as you wouldn't be able to retract the gear, thus you might not be able to continue your climb. I'll get into that more when we discuss multi-engine flying as it relates to World War II airplanes. Up front, there's a lot of firepower, 4 50 caliber machine guns, and normally a 20 millimeter cannon. There were some other configurations, but that's the standard setup. Now there's room for a lot of ammunition up there, up to 500 rounds per gun for the 50 cals and 150 rounds for the cannon. Among major U.S. frontline fighters, the P-38 was the only one to have a 20 millimeter cannon from very early in the war, and that's because the early U.S. 20 millimeter cannons were prone to jamming. However, the 38's configuration made it easy to clear the jams from the cockpit. So they kept the cannon in there and went with the hydraulic charging mechanism. Speaking of jams, the machine guns in the early planes would jam due to feeding problems at high G loads. They fixed that by staggering the guns, which is why in many P-38s you see the barrels are uneven in terms of the distance that they stick out of the nose. That's because they're staggered so they can have straight belts going in to feed the guns. The twin boom design also allows pretty easy installation of tricycle landing gear, and that was uncommon on World War II fighters. This was a big plus on a high-powered twin-engine airplane. We're getting near the end of the video here. I do realize I've left a lot uncovered. However, keep in mind this is just part of a series. I have a lot more I want to talk about in regards to this airplane. The next P-38 episode is going to cover the controversies that surrounded the plane. I'll get into the plane's technical problems, some of which were quite serious, and I'll explain how they were solved, at least solved in most cases. That should also dovetail into the reasons the plane was so successful as a fighter in the Pacific, but less so over Fortress Europe. I want to thank all my subscribers, especially my Patreon supporters who got early access to this video. I've added all P-38 manuals that I have to the Patreon section, and I've put good resolution images of the Hal Hubbard article with pictures and so forth in that Patreon section as well. And for the higher tier Patreons, I'll just put the whole magazine in there. For non-Patreons, I don't want you to be left out, so I'll post the rest of the article now, so just the text format, so you can pause the various pages and read it for yourself if desired. That's all I have for this moment. I hope everyone has a good day. I look forward to reading your comments, and keep an eye on this channel for the next episode. Thank you and goodbye.